Welcome. Today I'm going to talk to you guys about the rules that govern how we transfer the confidence in our measurements throughout a mathematical manipulation of those measurements. So it's not often in physics or in any science really where you just make measurements and then report out those measurements. Oftentimes you will do something with them, whether it's graphing or some sort of calculation. In this class, we do a lot of graphing, but we also do a lot of calculations as well. In fact, it's often the case that we take a measurement and then have to manipulate that measurement mathematically to be able to find a different quantity. So to do that, we need to take the confidence that we have in the initial measurement and then make sure it gets transferred through to the final calculation. It's important to remember that that initial measurement confidence has to be represented in the final calculation measurements as well. So let's go ahead and talk about that. Slide myself off to the side here. This video is 004, Confidence and Mathematics. We're going to whip through it real fast. I think you'll find that this stuff is pretty easy. It may even be a review for you if you had to do it in chemistry class. So let's go ahead and jump right to it. First, I'm not going to write anything on this slide. I just want you to see it. It's important to remember that there are rules, and those rules are developed by people who saw that there was a need to take the confidence that you had in your measurements and make sure it was represented in a final answer. In your math class, when you multiply two numbers together, you report down all of the digits that you get in your answer. Whatever your calculator says is what you report down. But that can't happen in physics because you only knew certain digits in your initial measurements, so you can only have confidence in a small number of digits in their final answer. And so it's important to remember that there's a vast distinction between math and physics. In math, it's okay to write down every digit because it's assumed that you know what those are. In physics, measurements are the basis of everything, and so the confidence you have in your measurements has to be shown in the confidence you have in your answers. So it's important to remember that as we do it. Now, what's interesting is, for reasons that we're going to get into in a minute, there's actually two rules. One rule for addition and subtraction and one rule for multiplication and division. They're not very difficult, but they are kind of important to remember the differences between the two. So I am going to go ahead and draw on this one so you can see. Let's say that we have a situation where we need to add three numbers together. Okay, and so those numbers are, let's say, 1, 2.34, okay, and let's say that's in meters. And then we have 1.654, and finally we're adding in together another 0.3, let's just say 0.3 meters. There we go. So we're adding these three together, and we want to come up with an answer. Now, I've lined up the decimals just like your third or fourth grade teacher told you to do, so that you can see this is the tens place, this is the ones place, this is the tenths place, hundredths place, and thousandths place. But you'll notice that there are some numbers here, like for example, this one doesn't have a hundredths, and it doesn't have a thousandths place. In your math class, you assume that that's a 0. I will tell you right now that if you're talking about actual measurements, the chance that that's a 0 is very small. And so in reality, if we were going to write something in there, we don't know what should go there or what should go there. We have no idea what those measurements should actually be. Could be anything. And the fact that it's a 0 in math class is kind of a cheat a little bit. For actual measurements, you really need to know what those things are. And if you don't, then they are uncertain. The same thing goes for this thousandths place right here. We have no idea what that is. If I'm going to go ahead and add these together, you're already going to see that there are some issues here. Now I'm going to add this in my head, so there's a first issue right there. Some number plus 4 plus some number, well, I'm going to assume that it's a 4, but I really don't know for a fact, so I'm going to put a question mark underneath it. Now don't feel like you're going to have to do this yourself. I'm just doing this to show you how this works. 4 plus 5 is 9, and then some question mark added to it. I don't know what that is. And then adding these together, we get 12, we get 3, oops, sorry about that. We get 4, and we get 1. There we go. So our answer should be 14.294. Now I'm going to go ahead and see, just to make sure, I'll check to make sure after this video is over that I got it right. But look at your answer here. We know it's 14. That makes sense, right? We know what these numbers all are. And we know what these 3 numbers are, so that we know that that's a 2. And so we know we had to carry the 1 as well. But when we got here, we honestly had no idea what this 4 plus 5 plus something should be. And so I reported what I knew, but in reality there's a lot of uncertainty in what that actual value should be because I don't have a number right there. It's probably going to be more than 9, of course, but how much more than 9, I have no idea. And it could very well be 9. I have no idea. That's the whole point. I have no idea what that value actually should be, and I have no idea what this value actually should be. So in reality, can I report out values that I don't know? The answer is no. So that number has to go away. This number has to go away because they have so much uncertainty in the actual numbers. I only know for a fact this is a 1, this is a 4, and I know that this is a 2, but I know next to it is a 9, or the part of it that I know was a 9. So I am going to have to round up if I'm not careful here. So my answer is actually the 2 places that I know, plus the 3rd place that I know rounded up because of the 9 factor there. So my answer should actually be 14.3 meters. Again, the 3 part comes from the fact that there's a 9 right there. Even though I'm getting rid of the 9, I still have to take that little bit of data into account. I know it's going to be 9 or higher, so I have to go ahead and round up. Anything 5 or higher would have to be rounded up, of course. Now, if you're one of those people who doesn't like to round, that's totally okay. You could write the same number down if you wanted to by writing this whole thing, 0.294, and then using the little trick with the overbar I talked about in the last video. Putting that overbar above the 2, which is our last significant figure, would be exactly the same thing. Those 2 are equivalent ways of writing that. So what's the rule here? Well, the rule is very simple. You eliminate any places that have any uncertainty in your problem. So here are my inputs. I have uncertainty in the thousandths place, and I have uncertainty in the hundredths place. So I have to get rid of those. So I take the farthest right point, like so. I take the farthest right digit, and then can only use that in my answer. So all 3 of these, I know for a fact that this is a 3 in the tenths. I know for a fact this is a 6 in the tenths, and I know for a fact this is a 3 in the tenths. So that's the last place that I can go ahead and write down with any confidence because of those question marks there. Hopefully that makes sense for addition, and it also works for subtraction as well. Moving on to the multiplication and division, you're going to see it's a little different. And in fact, it's actually quite a bit easier. So multiplication and division, I'm going to go ahead and swap out to get back to my blue here. Let's say that I'm going to go ahead and multiply 2 numbers together. Let's say 12.345, and we'll call that meters. And we'll multiply that by 2.6 seconds. There we go. So 12.345 meters times 2.6 seconds. So our answer is going to have units that are meters times seconds. So that's not really all that important for this. But I just want you to see what sort of uncertainty we have here. If I go ahead and multiply this out, I end up with a value that looks something like, and I can do this by hand if I wanted to, but I'm not going to do it by hand. I'm actually going to cheat a little bit and do it on my calculator phone thing here. 12.45 times 2.6 gives me 32.097. So my answer is this. In math class, everything's great, no problems, I'm done, turn it in. Unfortunately, this is physics. And this problem right here determines the fact that determines the fact for you that we have a very small confidence in this time measurement right here. Only 2 sig figs in the time measurement, whereas this has 5 sig figs in the length measurement. So there's a lot of lack of confidence here. And we have to take that into account in our answer. And so there's a very simple rule, and that is for multiplication and division, you just take the least number of sig figs in your inputs and use that for your answer. So as I was saying before, this value has 5 sig figs. This value has 2 sig figs, which is the least number. The least number is the 2, so in the answer I can only have 2 sig figs. So I can write that as a 32, if I wanted to, meters times seconds. Or I can use that trick we just talked about with the overbar, which is the 32.097, and then use the overbar above the last significant figure. That way I don't have to round anything off, so that it takes away all the questions for it. Oops, meters times seconds, there we go. Hopefully that makes sense. So again, the rule is to use the least number of sig figs from your inputs. Now, you might ask, well, am I always going to have to deal with such simple questions in this class? The answer is no. You're often going to have to deal with multi-step problems, but for a multi-step problem, it's actually pretty easy. So I'm going to show you that real quick. For a multi-step problem, you just have to remember to use your order of operations and then keep track of the significant figures that you have in the order of operations. So let's imagine for a moment I have 1.16 plus 1.2, and I'm going to divide that by 2.33. Okay. So what would be my actual answer in physics? So order of operations says I have to do what's in the parentheses first, right? PEMDAS, right? So the P is the parentheses. So I'm going to go ahead and add those two together. So I'll swap out my pen. I'm going to get this down here, and I'm going to add these two together like so. Now, do you remember what the rule is? The rule is if there's any uncertainty, I can't keep that digit. So if I add these two together, I end up with 2.36, but this digit right here is a total question. I have no idea what that's supposed to be. So what is that? Is that actually a 6 right there? The answer to that is no. I have no idea what it's really supposed to be. Could it be a 6? Sure. Is it probably not a 6? Yeah, it's probably not a 6. So I have to try to take that into account. So I only actually have significant digits for the 2 and the 3 there. So to write that out, I have 2.36 with an overbar above the 3. Why did I leave the 6 in there? Because I'm going to need that tiny little bit of information. I know that at least part of it was a 6. So I'm going to keep that 6 in there so that I don't have a lot of rounding error in my answer. So now I have 2.36 with 2 sig figs divided by 2.33. Okay. So obviously I know it's going to be close, just a little above 1, but just to make sure, I'm going to do it on my calculator, and I end up with this number right here. 1.012875554, and then it goes on, I think, but that's all my calculator will give me. So the question then is, where do I round it off? In physics, you should never, ever, ever ask that question, to what place do I go? Like you ask in math class all the time, because the significant figures tells you. So remember, the rule for division is to take into account the fact that you have a different number of sig figs. On the top here, you have 2. On the bottom, you have 3. And the question is, when you do multiplication and division, what's the rule? The rule is you take the least number of sig figs in your inputs and use that for your answer. And so the least number of sig figs on the inputs is 2, and so I can only have 2 places in my answer. So my answer is actually 1.0. And I don't know what the units are because I didn't give you those. Does that make sense? I hope that does. This answer will give you points off. It's just ridiculous. There's no measurement that has infinite precision like that. So you really need to make sure to take that into account. If you have any questions, please make sure that you pay attention when we do our practices, because the practice, we're going to do lots of practice rounds for this. If you haven't had a chance to practice it in your chemistry class, this is going to be your time now to try it. So I want to thank you for watching. Please don't forget to fill in your note sheet and the questions. Questions are actually kind of crucial for me, so I can go ahead and guide the discussion on the next day. We're also going to do some practice to make sure that you have it. Remember, this is something that you need to take into account every single time you make a measurement or make a calculation in this class. With that, I'm going to sign off. Good luck to you. I hope it goes well. I know that significant figures are a bit of a hassle, but sooner or later they do become like second nature. You don't even really think about it. You just do it. I hope that happens for you very soon. All right, good luck. If you have any other questions, let me know. Thanks.